to lecture 31, where we introduce a new concept, that of order of infinitesimal and infinite and their principal parts. So let's start by defining the order of infinitesimal. Okay, so this is defined for a function f. Let us given a function f defined in a neighborhood of the origin. Minus r is an interval, is an open interval around the origin for some r larger than 0. Okay? Now, if there exists a real positive number a and a real number c different from 0, such that the function f of x is equivalent to c x raised to the a for x that goes to 0, then we say that f of x is an infinitesimal of order a with principal part c x to the a. So this is the definition. Let's review what we just said. We are saying that if we have a function f which is defined in the neighborhood of the origin, and we can approximate this function with cx to the a, where c and a are real numbers, then we say that f of x is an infinitesimal, meaning that the function goes to 0, exactly like cx to the a goes to 0, and it goes to 0 as fast as cx to the a, which means that cx to the a is basically a reasonable approximation of the f of x, and for that reason is called the principal part. So let's immediately give some example just to see what we are talking about. Let's consider, for example, the function sine of x. Now, we know that sine of x is defined in a neighborhood, in any neighborhood of the origin, okay? And we also know that the asymptotic equivalent says that if x goes to 0, sine of x can be approximated to x, right? So we saw this when discussing the asymptotic equivalence, okay, for x that goes to 0. So this means that sine of x is an infinitesimal of order 1, just because this x is raised to the 1, and its principal part is exactly x. Let's give another example. Let's take now the cosine of x minus 1. You see, I'm not considering a cosine of x because cosine of x tends to 1 when x goes to 0. I need a function that tends to 0. And in fact, cosine of x minus 1 tends to 0 for x that goes to 0. And again, using the short expansions, we know that this is equivalent to minus 1 half x to the square for x that goes to 0. So we can say that cosine of x minus 1 is an infinitesimal of order. What is the order now? Well, the order now is 2, just because we have this exponent 2, and its principal part in this case is minus 1/2 x to the square. So you recognize that in this case c is just equal to minus 1/2. Let's consider another example now. If we have the hyperbolic sine of x, now we know that the hyperbolic sine of x tends to 0 and x goes to 0, but we want to establish now what is the order of infinitesimal of the hyperbolic sine of x minus x. And again, this is another function that tends to 0 for x that goes to 0, so it is an infinitesimal. Now, if we replace the hyperbolic sine of x with its Taylor polynomial, okay, we know that the Taylor polynomial is x plus x to the cube divided by 6, and of course there will be plus x to the 5th divided by 120, and so on and so forth, minus x. So the x's cancel out each other, so we can say that this is equivalent to x, to 1/6 x to the cube, right, plus little o of x to the cube, which says that the function hyperbolic sine of x minus x is an infinitesimal of order 3 with the principal part 1/6 x to the cube. Let's give a final example, and we'll see that this definition is not always easy to apply. It's not always to identify the order of infinitesimal of a function. For example, if we consider the function x logarithm of x, well, we know that when x goes to 0, this goes to 0. So yes, this is an infinitesimal. However, it is not easy to see what is the specific order. Well, there is no specific order of infinitesimal according to the definition. Let's make an observation now, because we may wonder if this kind of definition of infinitesimal can also be applied to sequences. And well, the answer is yes. So the same definition applies to sequences with x replaced by 1/n. For example, consider this sequence. Sine of 1 over n, right? For n that goes to infinity, of course 1 over n goes to 0, so sine of 1 over n is an infinitesimal. And we know that these can be approximated with 1 over n, right, all raised to the 1. So clearly we see that we have an order of 1 and principal part equal to 1 over n. A second example. Let's consider the sequence n plus 3 divided by n to the fifth plus 2, right? So we know that when n goes to infinity, this is asymptotically equivalent to 1 divided by n to the 4, right? So, and 1 over n to the 4 is another infinitesimal. It goes to 0 when n goes to infinity. So we can say that this is an infinitesimal of order 4 with the principal part 1 over n to the 4. So you recognize that c is equal to 1 in this case. Now what would be the formal proof of this thing? We can also provide the formal proof. Okay, and the formal proof is the following. We need to determine the limit as n goes to infinity, right, of n plus 3 divided by n to the fifth plus 2, all divided by 1 over n to the fourth, right? And this is just the limit as n goes to infinity of n to the fourth that multiply n plus 3 divided by n to the fifth plus 2, right? But of course this limit is just to 1. So this proves the fact that n plus 3 divided by n to the fifth plus 2 is asymptotically equivalent to 1 over n to the fourth. Let's now pass to the definition of order of infinite. Again, we have a function, but now we don't need to say that the function is defined over a neighborhood of the origin, but we just need to say that if the function f of x is equivalent to cx raised to the a for x that goes to plus infinity with some a real positive number and some real number c different from 0. Of course we are excluding the case c equals 0, otherwise the function would be equivalent to 0. So if these two conditions are verified, then we say that f of x is an infinite of order a with the principal part cx to the a. So this is the thing to remember. We say that f of x is an infinite of order a with the principal part cx to the a. And in fact, if we look at this cx raised to the a, this is something that will go to plus or minus infinity depending on the value of c. For example, if c is positive, cx to the a will go to plus infinity. If c is negative, cx raised to the a will go to minus infinity. It doesn't matter. In any case, we say that f of x has order of infinity a because it goes to infinity as fast as cx to the a. Also in this case, let's provide an example just to see what we're dealing with. Let's consider x to the fifth plus 3 divided by 3x squared plus 1. And we see that when x goes to infinity, of course these will be just like 1/3 x to the third, right? So we immediately realize that this is order of infinity 3 and principle part 1/3 x to the third. Now the formal proof of this, well, the formal is simply that we can determine the limit as x goes to plus infinity of x to the fifth plus 3 divided by 3x squared plus 1 divided by 1/3 x to the cube. Alright? But this is just the limit as x goes to plus infinity of, well, we have now 3 times x to the fifth plus 9 on top, and then we have 3x to the fifth plus x to the cube. And because when x goes to plus infinity, what really counts is the larger power, we immediately realize that this is just 1. Let's look at another example. Let's consider now x to the fifth plus sine of x divided by 3x to the square plus 7. Well, clearly when x goes to plus infinity, what really counts is x to the fifth at the numerator and 3x squared at the denominator. So we can immediately say that this is just like 1 x to the cube, right, divided by 3 for x that goes to plus infinity. So this is an infinite of order 3 and principal part 1/3 x to the third. However, the same function can also be considered as something that goes to 0 when x goes to 0. So it is also something that we can rewrite x to the fifth plus sine of x divided by 3x squared plus 7. Remember that when x goes to 0, what really count are the lowest powers of x. So these can be approximated to x on top, because sine of x can be approximated to x, divided by 7, right? And so this is an infinitesimal of order 1 and principal part 1/7x. To prove this formally, to prove this last thing formally, okay, so let's do this. Let's provide the formal proof of this. Well, we need to evaluate the limit as x goes to 0 of x to the fifth plus sine of x divided by 3x squared plus 7 divided by 1/7 x, right? But this is the limit as x goes to 0 of what? Well, we need to multiply the numerator by x, right? So we'll have we need to multiply by 7. So we have 7x to the fifth plus 7 times sine of x this is what we get at the numerator. And then we have 3x to the cube plus 7x at the denominator. And, well, this is just for x that goes to 0, we can immediately neglect these, the highest power, and we're just left with something that can be approximated to, we can use the equivalence, asymptotic equivalence. We can say that this is simply 7x plus little of x divided by 7x plus little of x. So this is clearly 1, which proves that indeed 1 over 7x is the principal part of this infinitesimal. Let's go back to sequences now, and let's consider this sequence an equal to 1 over n squared sine of 1 over n minus 1 over n hyperbolic sine of 1 over n squared. Now, it's not difficult to see that when n goes to infinity, let's see what happens. Well, when n goes to infinity, we have that this will go to 0, and sine of 1 over n, this will go to 1 over n, which again will go to 0. And also this will go to 0, but also the hyperbolic sine of 1 over n squared will go to 0. So clearly an is an infinitesimal. Okay, so we can conclude that an goes to 0. So it is an infinitesimal. But what is the order? Well, we don't know that. Okay, so clearly establishing the order means to make some kind of expansion of Taylor polynomials to transform this sequence into some form of polynomial. And we know that when dealing with the sequence, the first step is to set 1 over n equal to x. Why am I saying 1 over n? Because we are dealing with infinitesimals. So when n goes to infinity, 1 over n is x that goes to 0, right? So if we do this, what we get is x squared sine of x minus x hyperbolic sine of x squared. And now we can use the Taylor expansions, because we can expand sine of x when x goes to 0, right? So this will become x minus 1/3 x to the cube, and I would say that we can stop here plus little o of x to the 4th, right? And minus x, then we need to expand sine of hyperbolic sine of x to the square. So let's briefly recall what is the expansion of the hyperbolic sine of t, let's say. Well, the hyperbolic sine of t is t plus 1/3 t to the cube plus, well, we have little o of t to the 4th, right? Now, because we need to expand hyperbolic sine of x squared, we will replace t with x squared so that we get the hyperbolic sine of x squared will become x squared, right, plus 1/3 of x to the 6th, right, plus little o of x to the sixth. So these are basically the results that we need to use. Okay. Now, consider one thing. Uh, uh, because we are looking at an infinitesimal, we know that we want to focus on the lowest power of x. So the first term that will be not cancelled by our Taylor expansions is the one that counts. So instead of expanding the hyperbolic sine of x squared up to this term, I will stop here because we'll see that this is the only term that will be cancelled from the first one. So let me do this and I'll come back to this explanation. So my decision is to expand hyperbolic sine of x squared up to the first term. So we only take x to the square, and of course this will be little o of x to the fifth, because we know that the next term, now you see how simplified is this new expression, because we started from this very long expression for an. We had sine, hyperbolic sine, but now we know that this sequence can be just approximated to this principal part when n goes to infinity. And on top of that, we can build even more sequences. For example, let's see what happens if we want to multiply an times a power of n to some exponent alpha with alpha any real number. Okay, so what we have is an. Well, we can write this down. We can write an divided by 1 over n to the fifth times 1 over n to the fifth times n to the alpha. Okay, I've just divided and multiplied by 1 over n to the fifth. But now, because of what we said of our result, that an is equivalent to minus 1/3 n to the fifth, we know that this will tend to minus 1. There was a mistake. I'm realizing now that I made a mistake in the previous calculation. This is not 1/3, but of course this is 1/6. Okay, so this needs to be changed. Sorry, 1/6, and this is 1/6. Okay, so this is 1/6, and this is 1/6. Okay, so what we can say is that this limit now is simply minus 1 over 6, right? So finally, we can say that this new sequence, an times n raised to the alpha, will tend to minus 1 over 6 times n to the alpha minus 5. So depending on the value of alpha, we can see what is the behavior of the sequence. Now, when using this technique of infinitesimal or infinite, it is very easy to fall in some traps. For example, let's consider this limit. Limit as n goes to infinity of this sequence, cosine of n minus 1 divided by n squared. Okay. Now we might think, okay, why don't we just apply the Taylor expansion to the cosine of n? Well, but we cannot do this, right? So let me write this in red. No Taylor expansion for n that goes to infinity, uh, because clearly we have no way of expanding the cosine of n. We would need n to go to 0, right? So we cannot use the expansion like cosine of n equal to 1 minus n squared divided by 2. No, 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 this is totally wrong. Okay, this is totally wrong, just because the cosine of n is not an infinitesimal for n that goes to infinity. One thing. And also it would be also a mistake to take the limit of x. We might think, okay, this looks very much like the one of the fundamental limits, but the fundamental limits is limit as x goes to 0 of cosine of x minus 1 divided by x. So once again, you see that this is only valid. Let's consider another sequence depending on a parameter. Let's evaluate the limit as n goes to infinity of 1 minus 5 over n all raised to n raised to the alpha. Okay, for alpha some positive real number. Okay, and we see that this limit is of the form, well, when n goes to infinity, 5 over n goes to 0, so the base will become 1, and the exponent n to the alpha for alpha positive will go to infinity. So this will be one undeterminate form. And we know that this is one of those series of the form an raised to the bn, and we know how to deal with this series, okay, with the exponential transformation. So this is just equal to e raised to the logarithm of an to the bn, which comes up in front. Okay, so we can rewrite this, so we can rewrite 1 minus 5 over n, all raised to the n alpha, okay, as e raised to n to the alpha times the logarithm of 1 minus 5 over n. And because for n that goes to infinity, 5 over n goes to 0, we can expand this into e raised to the n raised to the alpha, and instead of the logarithm of 1 minus 5 over n, we can just write minus 5 over n. Okay, so this is just a very quick way of seeing what happens, and this is just like writing e to the minus 5 times n to the alpha minus 1. And this is what we need to establish the behavior of the sequence depending on the value of alpha. In fact, we see that if alpha is equal to 1, right, so the sequence is just e raised to the minus 5 times 1, so this is just e to the minus 5. So this is the final limit, okay, of the sequence as n goes to infinity. Let's see what happens if alpha is larger than 1. Okay, if alpha is larger than 1, then we have that e to the minus 5. Well, because alpha is larger than 1, alpha minus 1, the exponent, is going to be a positive number. So for n that goes to plus infinity, this will multiply plus infinity. So this implies that this will just tend to 0. Okay? If instead alpha is less than 1, we have that what? Well, we have that e to the minus 5. Now alpha minus 1 is a negative number, so this will be multiplied by 0. So this will be exactly 1. Okay, so this is a very quick way of looking at the sequence for n that goes to plus infinity and just using the order of infinitesimal, well, or if you like, the Taylor expansions are just two faces of the same coin. If we Another interesting example is the following limit. Let's say we have the limit as x goes to plus infinity of 1 plus 1 over x all raised to the x minus e, and this is now multiplied by x. Okay, and we recognize the definition of e, and we immediately see that well, this term here, basically this term will tend to 0 because 1 plus 1 over x raised to the x, for x that goes to plus infinity, is just e. E minus e is 0, so we have an undeterminate form of the type 0 times infinity. Okay, now we might want to use Taylor, okay, to solve this limit. However, we cannot use Taylor because x goes to plus infinity. So we know that Taylor works when we have x that goes to, or the variable that goes to 0. So we can make the change of variable 1 over x equal to y, so that when x goes to plus infinity, y goes to 0 plus. Okay, let's see what we get. Well, then we have the limit as y goes to 0 plus of, well, we have 1 plus y, all this raised to the x, which is 1 over y, minus e, and all this is multiplied by 1 over y, okay, which can be rewritten as limit as y goes to 0 plus of, well, we have 1 plus y to the 1 over y minus e, all divided by y. Okay, and at this point we may recognize some fundamental limits. Remember that limit of the form e to the x minus 1 divided by x for x that goes to 0. We might think of something like this. Okay, so we may want to replace this term with the exponential transformation. Let's see what we get. We have now limit as y goes to 0 plus of, well, we always have y at the denominator, right? And well, we can rewrite this as e raised to the 1 over y logarithm of 1 plus y minus e. Okay, so this is the new form, which is something not actually the fundamental limit, so we need to put some e to factor out some e, right? And but we can do this after developing the logarithm of 1 plus y. We will expand the logarithm of 1 plus y, because we can do this since we have that y goes to 0, right? So we can expand this logarithm. Let me do this. Okay, let me expand this logarithm. This will become limit as y goes to 0 plus of, well, of course we have y here, right? And we have e raised to the 1 over y, and instead of the logarithm, we will be expanding the logarithm of 1 plus y into y minus 1 over 2 y squared plus little o of y squared. Why did I stop at the second term? Because we immediately see that when there is an e now coming out that will be factoring out. So let me show you this. So this, if I develop the multiplication, what we get? We get limit as y goes to 0 plus of, we have y here, and we have e times e to the minus 1. In the next example, we would like to use what we have learned about the Taylor expansions to expand the tangent of x. Now, in the following example, we would like to expand tangent of x around x naught equal 0 up to the order 6. In fact, this was one function missing in the Taylor expansions that we presented in the previous lectures. Now, there are two ways of doing this. Of course, the first way is just compute the derivatives of tangent of x in x naught equals 0 up to n equals 6. But there is also another possibility. And the other possibility is writing tangent of x as sine of x divided by cosine of x and replacing sine of x with its Taylor polynomial, cosine of x with its Taylor polynomial. Okay, let's see what we get. Well, let's first expand sine of x, and then we will write cosine of x to the minus 1. So this will be sine of x and this will be cosine of x. Okay, good. Now, sine of x is x minus 1 6 x to the cube plus 1 over 120 x to the fifth, and of course this is where we need to stop, right? Because we know that we need to expand up to n equals 6, and the next term is going to be x to the 7, so there's no point in moving forward. So we will just write little o of x to the 6. For the cosine of x, we have 1 minus 1 half x to the square plus 1 over 24 x to the fourth. And well, let's see what happens if we stop here. Okay, so let me stop at x to the fourth and write little o of x to the fifth. Okay, and we'll see the reason why we'll stop at x to the fourth in a few minutes. But now we have a problem, because we need to take the inverse of the Taylor expansion of cosine of x. And now we remember one of the formulas that we gave when introducing the Taylor polynomials for the first time, and that formula was 1 plus t to the minus 1 equal to 1 minus t plus t squared minus t cubed, and so on and so forth, right? So we will be using this now. And so this is the formula that we will be using. Now, if we apply this formula to this expansion, so let me copy this here. Well, what we have, we need to write this to the minus 1, okay? all this to the minus 1. And notice that we can consider these to be plus t, right? So this becomes 1. Well, we need to write minus t, so we need to change the sign of each and every term, plus 1/2 t squared, x to the square, minus 1/24 x to the 4th. Okay, so this is simply minus t. Well, now the next term should be plus t squared. Okay, so when doing the square of t, we notice that we definitely have 1/4 x to the 4. And now every other term will be will have a power of x larger than x to the 4, which it is something that we can immediately neglect. Okay, why is that? Well, we can neglect this because we know that all these terms will be multiplied by these first Taylor polynomial sine of x, so they will disappear anyway. So I will be stopping here and will write little o of x to the 5th. So as you see, this was the reason why we stopped the expansion of cosine of x up to 1/24 x to the 4th. Now let's simplify this expression that becomes 1 plus 1/2 x to the square plus 5/24 x to the 4th plus little o of x to the 5th. Now we are ready to put everything together, and we have that the tangent of x is equal to the sine, that is x minus 1/6 x to the cube plus 1/120 x to the 5th plus little o of x to the 6th times 1 plus 1/2 x to the square plus 5 divided by 24 x to the 4th plus little o of x to the 5th. And now we can expand the product, and we have x plus 1/2 x to the cube plus 5/24 x to the 5th. Then we have minus 1/6 x to the cube, and we have, of course, the other product of minus 1/6 x to the cube, but the other terms can be neglected, so we can just move to minus 1/12 x to the 5th plus 1/120 x to the 5th plus little o of x to the 5th. And now after writing x, we see that we have the terms in x to the cube, or this one and this one, that will provide 1/3 x to the cube, and then we have the terms in x to the 5th that will provide plus 2/15 x to the 5th plus little o of x to the 5th, which concludes the expansion. Now there is another way of obtaining the Taylor expansion for tangent of x, and I will present this as the last example. So let's say that tangent of x, we know that tangent of x is an odd function, so its Taylor polynomial will only have odd powers of x. So it will be something like x plus a x to the cube plus b x to the fifth. And let's say that we stop at the fifth order, so we have little o of x to the sixth. Now the problem is, how can we determine a and b? Okay, and we will check at some point that these coefficient will be just like the ones that we have identified in the solution 2. Now the trick is the following. We can write tangent of arc tangent of x, which is simply equal to x, because these two functions are one the inverse of the other. And the idea is that now we can use what we have learned about the polynomial of compound function, and we remember what is the polynomial expansion for arctangent of x. And is the following, is x minus 1/3 x to the cube plus 1/5 x to the fifth, and so on and so forth, right? So we will be using this result. So let's write this equation. X, we said that this is equal to the tangent of arc tangent of x, and by using the first assumption, right, by using this assumption, we can rewrite this as arc tangent of x plus a times the arc tangent of x to the cube plus b times the arc tangent of x to the fifth plus little o of arc tangent of x to the sixth. Okay, and now we will be using the Taylor expansion for arctangent of x. So we have x equal to, well, the first arctangent will be expanded into x minus 1/3 x to the cube plus 1/5 x to the fifth. Then we have plus a times, we have x minus 1/3 x to the cube plus 1/5 again x to the fifth, all raised to the fifth power, this is to the third, plus b times x minus 1/3 x to the third plus 1 divided by 5 x to the fifth, and this is now raised to the fifth, plus, well, this little o of arctangent x to the sixth can be easily proved to be nothing else that little o of x to the sixth. I will leave this as an easy proof. And now we can immediately realize that, let's expand some of these terms. Okay, so we have x equal to x, and which terms will survive? Remember that we need to expand up to the order 5. Okay, so of course we will leave 1/3 x to the third plus 1/5 x to the fifth, but then from this power, from this, what will survive will be a x to the cube. Okay, and of course when we take the cube of 1/3 x to the third, we get a power 9 of x, which will be beyond our interest. So the only thing that will survive at this point is going to be the double product of x and minus 1/3 x to the cube, which is basically minus a x to the fifth. Okay, and for the last term, of course, the only thing that will survive is just b x to the fifth, and we can write now little o of x to the sixth. So Finally, we can rewrite this as by just simplifying this x and this x. What we have is that 0 is equal to, well, we have minus 1/3 plus a times x to the third. I'm considering now these two elements, this element and this element. And then we have plus 1/5 minus a plus b x to the fifth plus little o of x to the sixth. And now we have two equations that can be derived by just applying the identity of polynomials. We necessarily have that minus 1/3 plus a, right? So this must be 0 because on the left hand side there is no coefficient for x to the third. The same way 1/5 minus a plus b must be 0. Now from the first equation we get that a is equal to 1/3, and now we can replace into the second equation and we get the b is equal to minus 1/5 plus a, which is 1/3, and this is minus 3 plus 5, so this is nothing else than 2 divided by 15. So we can conclude saying that the tangent of x is equal to x plus 1/3 x to the cube plus 2/15 x to the fifth plus little o of x to the